So it's my great pleasure to welcome Angjoo Kanazawa. So Angjoo Kanazawa is an assistant professor at the EECS department at the University of California at Berkeley. Her research is at the intersection of computer vision, graphics, and machine learning, focusing on visual perception of the dynamic 3D world behind everyday photographs and videos. And Angjoo won many awards. So she has been named a rising star in the EEC Electrical Engineering Computer Science and is a recipient of the Anita Borg Memorial Scholarship, Best Paper Award in the Eurographics 2016, and the Google Research Award 2021. So without further ado, Angjoo, the stage is all yours.
Thank you so much for the introduction, and thank you for inviting me. And it's so nice to see everybody, at least virtually. I really hope next CVPR we can do this in person. Okay, so today it seems like everybody's talking about really cool applications of SMPL, and I want to talk about this aspect of visual imitation that SMPL enables us. So to begin with, I want to take a step back and go back to a really core point of why we are all looking at humans. And that is because since the dawn of civilization, we have functioned in a society where we spend our lives interacting and interpreting other people. And that is the setting in which we live in. And so this is why, at least for me, I think the ability to perceive humans, perceive, interpret, and interact with humans and their environment in the 3D world, I think is really going to be the key towards future of anything that we would really like to do. And so this is why I'm really excited about this topic. And because of the nice morning tutorial, I don't have to talk about all the backends, but the thing that I really excited about, or what a lot of my focus has been to do this 3D perception from images in the wild, which is the jargon that we talk about, to talk about images that are taken casually, like from your photographs outside your lab. Okay, so it's kind of a good contrast with the previous Microsoft talk. So a lot of my work, as you may have seen from the morning ones, have focused a lot on reconstructing humans parameterized by SMPL from everyday photos, like Coco's or these complex photos or videos. And so as we've seen, this really opens up, in particular, in perceiving humans in videos, in the wild video, really opens up a lot of paths. One of which, that I want to talk about is this aspect of how can we learn like this baby. So this baby is watching Rocky, and then he is imitating the motion, and it's on a TV screen which is flat, but clearly the baby is able to perceive the underlying 3D motion and imitating it. And so how do we do this? Now, if we can do 3D human over time and perceive them, is that it? Well, so perception is really not the end of the story. So methods like HMR or HMR and Vive would give you these asimple parameters from the images, but that is the step one. And then you really need to, in order to act and imitate it, you actually have to actuate your body, which might have a different topology for these, which has different topology for these virtual agents. They need to actuate their bodies in order to get to the pose. But this control problem is a really challenging one that even babies also struggle. So here's a baby trying to imitate his dad, and it's kind of there, but it's, needs a little bit more training. So this is an interesting problem in RL, and past work have started bypass the images and started working on mocap, in which you can parameterize this problem as a reinforcement learning problem. So given a character in simulation that you want to actuate, you have these reference motion that you get from motion capture. Okay, again, in order to actuate these simulated characters, you need actions, while mocap only gives you a recording of joint angles. It doesn't really tell you how to move them. Therefore, this is because you don't have the labels for the action, you can pose this as a reinforcement learning problem and do this imitation where you can train this agent to imitate it using the reward, which is how close is the final pose close to the reference motion. Now, these people, though, are working with motion capture, but the world is so much more than the green screen. So let's expand the world to YouTube videos of people doing these acrobatic skills. And so this is the work that we presented in SIGGRAPH 2 years ago, where the goal was to recover temporal smooth mesh recovery. Back then, there wasn't any HMMR or Vive, so this was more like a post-processing way of taking HMR outputs. And then you can use this as a target to train this policy, in which you can, this isn't just simply playing the angles. You can see that you can also train this agent to do the same action, but in a different environment, showing that this is, it's not just copying over the angles that you get from this. So because I don't necessarily want to really focus on the RL aspect, but I'm going to give a little bit more background into what is happening. So the bodies of the humans are represented by these states that are based on these variables of the body, like the displacement between the roots. And then there's a policy that takes in the state and outputs the action. And the action in this case actually is a target for the PD controller of where the joints should be. And then the reward is the motion tracking objective, which is to make sure that the pose of the character at time t is the same as the joint location recovered by this human body model. Okay, and then in this setting, please remember that is one policy per task, where the task is to imitate a specific motion trajectory. Okay. So here are some more results showing this, and it's really interesting to see the recovered 3D body next to the policy, because the policy's motion is much better, and this is because it's actually trying to do this in a physically simulated environment, and so the physics really helps you to fix some of the noisiness that comes from predicting humans in the video, which is a challenging problem. And again, because this is trained in an RL framework, which starts from like really bad motion, it's pretty robust at recovering from these perturbations, and we can throw boxes at it. Okay, so we did this for many videos and learned these skills. Here are some of this is probably my most favorite result. So one of the, it doesn't always work. So there's an interesting failure case where the reconstruction from the video on this particular dance sequence seems quite reasonable, other than the fact that like the hands are intersecting, but the policy wasn't exactly able to train this, and it's possibly because such nimble actions are still difficult, and it kind of comes to the question of how do you formulate the reward of when is it close enough. Okay, but training these policies per action sequence really allows you for fun applications like this physics-based motion completion. So what we have is all of these skills that we learned from the YouTube videos, and all of these are policies. Now we gotta have a target image that we only have a single image. Now we can reconstruct, we can run HMR on this image. We can run HMR on this image, and then figure out the pose that are closest in the reference data set that we have. And then we can just take the policy and initialize it with the target image's pose, and then play the policy forward, and then bring that sets of joint angles back into the image space into simple, which allows for this type of physics-based motion completion. Which is a cute application of this. Okay, so I do want to talk about more recent work, and I want to do a quick preview of what happens to these the latest advancement or latest approaches in this type of motion reinforcement learning-based animation approach. Instead of the policy imitating one specific motion, we have a recent work that will be presented at SIGGRAPH 2021 this year, which actually, if you took a course or tutorial on HMR, it's a very similar idea. So instead of having a single policy imitating every single trajectory, every single motion, in this case, we're gonna use multiple motion sets examples as real set of possible plausible motions. And then we're going to have a discriminator that says, instead of motion tracking that says, every single time the pose has to be this, we're going to replace that altogether with a discriminator that says whether the motion is realistic or not. And what this allows you to do is to train a multiple task, like this heading task, going forward, right, and left in a goal conditioned formulation, while restricting the motion to look natural. So I hope that sounds very much like, HMR, because you have all these reference motions and you do the simulation motion and then you send it to a discriminator which says it's real or not, and that is the style or the prior for the motion. And then you use another task that's task dependent reward, such as walking and such as punching a target. Okay, so that's one. But then the data set of motion priors involve people walking and people punching, but never like walking and punching together. But the network can figure out the right sets of motions, and so you can do fun things like having a zombie soccer, so where the task is to put the ball into a target. And then if you replace the motion examples with these zombie motions, then we get this zombie walk. The nuances of the impact of this is, perhaps outside the scope of this work, but really, this really combines multiple skills like running and leaping and rolling, which are all in the data set. And we don't need an extra hierarchical controller to combine multiple skills in order to perform this. And so this is an update, and it really makes a lot of these imitation learning approaches, the code base is simpler now, and then it's all available. So perhaps you might, if you're interested in the RL-based animation direction, you might want to check this out. Okay, but what is next? So this is all cool. We can imitate people from video. Is that really it? And that's not really it, because again, going back to this baby, there's a lot of imitation beyond body control. And this is a really nice clip from Andrew Meltzoff at the...
And Alan Alda puts beads in the cup. The little baby's too young to speak. We don't use language. She just watches us. Emotion. She's happy at what she did, but...
Okay, so like you can see, there's all different kinds of imitation, where it's not just the human body, just the body, but actually people interacting with the rest of the environment. And I think that's where really the exciting direction of learning from visual observation is. And so for that, we really need to be able to perceive the world not just as human bodies, but humans in the context of its environment and other objects that they are interacting with. And so really, I think what's the next step is to reconstruct humans and objects together in the wild. And so we could get a result like this, where you have these objects that are interacting with humans that are recovered. Okay, and before I talk about this work, I want to say that there's a big inspiration coming from these two works. One is on multiple human reconstruction, because it's similar. Multiple humans and objects have very similar approach. And of course, this Proc's work from Michael's lab, which is one of the first work that started thinking about objects and humans. In this work, there was scans of the environment available, and then the setup that we're interested in is that of in the wild. And this was a paper that was presented in UCCB 2022. So we want to reconstruct the humans and we want to reconstruct interacting humans and objects in the wild, and we don't have any 3D scans. So what do we do? And so what is really the challenge when it comes to this problem? Well, it is the same as always, which is that there is an immense amount of depth ambiguity. And when we show you the results of this, you're like, of course, that's the right result. But there are many different ones. One of which, for example, could look like this, or it could look like that. And they both completely explain, when you project these meshes, they look exactly the same. But you will notice that the top interpretation, the person is floating from the the couch, not the couch, the bench, as you can see in the top-down view. And so this is really the fundamental scale ambiguity when you come to 3D and 2D. And let's kind of dive into this a little bit more, because it's about placing the objects. And so given this camera and this image, there are possible 3D interpretations. We could have super tiny surfboard that is really close to the camera. Or we can have a really, really big 10-meter surfboard that is really far away from the camera, and then the person is floating. Okay, so anything, and either of them explain the same, reach to the same 2D projection. And so everything along this line is an infinite possible 3D interpretations of how the surfboard is interacting with humans. And so how do we really disambiguate this? Like, if you're only looking at the objects alone, it's very difficult to disambiguate this. But as humans, we can do this very easily. And I say it's because of two cues. First is that, we have a common sense object prior. Surfboards are not 10 meters or 10 centimeters. Right? So there's some expectations of what the surfboards are like. Second, we know that humans and objects interact. And so, especially when it comes to human like surfing, although we don't necessarily use these action labels, although we could, we will see that, they have to touch. And this really gives you some more constraints about where the object can be. Now, one other challenge, and where simple comes really nicely in this picture, is that, as you may recall from your geometry or class, that whenever you do, Hartley and Zisserman, whenever you do 3D reconstruction, you always have this one ambiguity in scale, because it could be any scale. You could have scaled the world, you could have scaled the object. So, for example, suppose somebody gives you a 3D reconstruction or 3D CAD model of a surfboard, but it's essentially unitless. It's in this, you can scale it in any way. And so, when you even start talking about, what is the common sense, but like these CAD models don't have any real units. You have to align them to units. But the nice thing about simple is that once you start reasoning about humans and objects together, simple is endowed with an actual metric space, because it's an actual scale shape space from all the scans. And so it actually has a height, and as you know, maybe the average simple body model is 170 centimeters. And so once you start reasoning about once you start put the human in the scene as a simple, it really fixes the metric scale in which we operate in. And so we can start saying things like, oh, the surfboard should be 2 meters. And that is actually meaningful now. And so really, this is why simple acts as, it's like the shape prior that you have in simple that doesn't come in ordinary surfboards, but we can actually endow it through simple. And so to put them in the same world, we're going to scale this, CAD models with some amount, and then we call this intrinsic scale value. And in order to incorporate the common sense knowledge, we introduce a shape prior, where a simplest shape, common prior is that, we Google on the internet, how big are surfboards? And the Google search says, well, surfboards are like 1 meter. And then we can scale it, and we can start with this, and we can use it as a mean. It's a very simple shape prior for this. And then later, we actually update this prior of the mean from the empirical distribution from the data that we reconstruct, which is a little bit like visual common sense learning, like learning what the common sense are from reconstruction. But I'll get to that later. So the overall method is very much like simplify. It's an optimization-based approach. So given the input image, you reconstruct the humans on every single bounding boxes. And then we will get instance segmentation on these objects, and we actually fit the object. And so here again is kind of embracing the simple approach where we use these object templates. And then the goal is to put them together. But the naive composition of these objects, starting from their average shape, is that they are, it has all these issues. So we're going to send it to this joint optimization, FOSAC, we call it for people, human object, spatial arrangement, in which we can do these global reasoning. Okay, and then fix it. All right, so let's jump into this. And really the key of this approach was to really kind of, 3D object reconstruction is really hard, especially in the wild. It's interesting because non-rigid things are hard, but rigid things are even harder because there's so many more different variations in the world. And so really the message from this work was like really embrace the CAD models for now. And then we can go with this, where we will start with one of the CAD models. Actually, if there are multiple exemplar mesh per that category, then we just try all of them and see which one minimizes the differentiable rendering loss the most. So we have this instance max and this exemplar mesh, and then you just do it just like simplify. You optimize for these parameters, and then you start from somewhere, and then it gets in there. As you might know, optimization is very, very sensitive to initialization, and so we have to initialize it with many different poses, and then we pick the best. Another component in the wild is that, or not even in the wild, when you start considering humans and objects, well, what happens is that often objects are occluded by humans or other animals like these dogs. And so you don't really want to penalize it. And then the nice, interesting thing is that these semantic segmentation methods give you modal masks, as in it will give you not a complete mask, only the seen portion. But then it also predicts the other objects. So it's really, all I'm saying is that just don't penalize it. Don't penalize the reconstruction loss on the silhouettes if there's another silhouette that's belonging to another object in front of it. And this is simple, but if you don't do this, it's going to, optimization is going to try to explain away these holes. And so these are, small but important things. Okay. Altogether, we just do a joint optimization and all of these things, and this starts to look like simplify. So there's this occlusion aware silhouette loss, human object interaction loss, which is very similar to prox, which is inspired by prox, the scale prior from the common sense of Google, and then making sure that the ordinal depth order is agreeing with your ordering of the semantic segmentation. And of course, you want to avoid the interpenetration. So for the interaction, we take the same path as prox, where we paint all these bodies and the CAD models as to where they could interact with. And first, we have to identify whether the human and object interaction is happening. And we do so by simply nearest neighbor of the box, like overlap of the boxes. Like we could have used some action labels, but what we do is do a naive reconstruction, initialize the scale of the object to the Google Common Sense value, and then figure out how much overlap there are. And if there are enough overlap, then you insert this loss, which attracts these objects to come close together. Okay, and so this is yet another reason in the importance of initializing a reasonable scale factor. Because if you start off with a reasonable size of the surfboard, then you can identify that they're probably interacting. But if it's super far away, then you can't. One interesting thing is, after running all our algorithm on all the images of Coco, you can actually look at the distribution of the final shape of size of the objects, right? Because you start off saying that the surfboards are 2.5 meters, but as you do this optimization, you're going to make them bigger or smaller. And then this is the kind of distribution of the sizes of these objects that you get from empirically fitting the model. And I think this is a really interesting kind of data. This is like statistical data on the shape, 3D shape and the size of the objects from 2D images alone, which is not possible to obtain without having a human involvement. And so this is like the, reasoning about both humans and objects together actually allows you to get more information that you couldn't have gotten if you only focus on objects or only focus on the humans. And that's the empirical mean that we learned by FOSA we obtained. Okay, so I just want to show some results and more results. And all the code is available. And then there's a nice collab that Jason made. And more recently, we are moving on to hands and objects following the similar approach. In addition to all these terms for the hands, we also incorporated the grasp prior from grab, that really gives you the final realism when it comes to interacting. And we also use this approach to collect the new data set, which is going to be out in a month or so, where we collected like, it's not a really, really big one. It's like 500 images or so, but it has a really rich interaction and really wide variety of object types. And then a super long tail of these objects that you can see. When we reconstructed keyframes from 100 Days of Hands and Epic Kitchen. It's an amazing, great data sets. Now, I also want to talk about say that like humans and objects and manipulation is another interesting aspect for really good place where visual imitation could be useful, but really another kind of imitation is how humans interact with other people and these social priors that exist within ourselves, or long-range behavioral patterns that people exhibit. And we don't really have that much data on this. And because it's you have to have a storytelling like data. And so for this, I think movies are really good domains, but movies are really challenging because there's a lot of cuts and existing methods don't really work that well. And so more recently, we started reconstructing movies. I talked about this work in yesterday's workshop at 3D Understanding. Hopefully there's some, if you're interested, please check out that recording. Okay, so as a takeaway, simple or reconstructing simple in the wild from videos really allow for this video imitation. And the low dimensional nature of simple is great for imitation. So I also have other works like this PyFu, which allows you to reconstruct my photo from a single image. But this is kind of a topology-free method. And while it gives you nice graphics, unless you have these joint angles are joint or these low dimensional representations very important for imitation. And so simple is great for this. And so I really think there's like a graphics use and more robotics or recognition use. And I really like simple for that, recognition and robotics use. So, and towards more complex imitation, we really want to look at humans and objects together, in which case we can embrace the CAD templates for now. And I'm looking for all these other object-based approaches. And then for rich behavior data source, I think movies are the new frontier. All right, with that, I'd like to end my talk and take any questions. Thank you.
Thanks, Angjoo, for the amazing talk. Lots of inspiring work. So there's multiple questions in the chat. So Gerard asks about the data in the wild versus expensive capture studios.
Or maybe Gerard.
Yeah, maybe I can. It was just to hello, Angjoo. Nice hair color.
Thank you.
Yeah, thank you for the talk. Like really cool. I mean, because we're following your work, I already knew everything. So yeah, I have a question about like I want to get your views on, because so the thing is like in the wild, like there's so many ambiguities that the signal to noise ratio is quite low, right? And so what do you think is how should we approach this problem of like capturing humans and objects and so on? Do you think we should capture a bit of data with high quality? I mean, Michael has captured this like very nice graph data set, but then you can probably do something in the wild, annotate data, I don't know, like some manual fixing. How do you see the road? Because we're definitely, I mean, optimizing the scales and so on is a really good first step, but we definitely need like to capture this data. And how do you see it? Like,
Yeah. No, this is a great question. And I think the answer is both, because we really embrace both. Because in the hand data, handwork, we use the grab net, which is trained on grab, which involves these motion capture data of the humans and objects. And we needed that to get the prior, because we need prior from somewhere. And so I guess I benefit a lot from these nice data sets that are captured in the mocap. And I'm not saying we shouldn't really do it. I just, some of the priors needs to come from there, but I just really like to look at real images, because that's what the problem is. I think my priorities, the way I think about it is like use everything that is available, but really try to look at real images. And it would be really nice if you can learn from real images. And this is why I keep on thinking about more like active sensing type perceptions, where multi-view signal could replace it perhaps. But I think it's both. I think it's definitely a balance.
Yeah. So one question about this, I think I agree fully with what you answered. But then, like, so the problem with images is that with the algorithm, when the algorithms are still not good enough, there's not much signal you're getting out of the images, right? So how do you see, like, do you see some annotation that we could, I don't know, like have some humans like fixing some tracking results, or I don't know, like something where.
Yeah, I mean, for certainly like for this hand one, we took the real data and then we basically use simplify, and it has lots of knobs. And so human in the loop, you can adjust it and get like a pretty good data. And that could be like your pseudo ground truth where you can like actually start with. And I think that's fine. But I think another thing is really to look at new kind of data and being a little bit creative about it. Or like not creative, but I'm not. It's like you want to look more. I'm saying in the wild is actually really big, and maybe there's a lot more data to be had.
Yeah,
I mean,
like this squeeze challenge, right? Or how is it called? Like this challenge where everyone was frozen and they
yes,
used it.
exactly. All these creative things like that. I think that would be nice. Yeah.
Oh, thanks.
Thank you for the question.
Yeah, another question is a suggestion. Maybe it's possible to combine image captioning and 3D human object generation into multitask problem to fix some of the depth issues.
Yeah, I think that's a really cool idea direction. And I think interaction going in that direction, also in movies, really opens up all sorts of these multimodal cues. And I'm like very all for that. Yeah.
Super. And the last question is, it's a question about human object interaction work. My understanding is, the question goes like that. My understanding is the human object interaction label helps a lot in the fitting process. I wonder if you have any thoughts on weekly supervised learning of human object interaction without relying too much on annotation?
Yes, but this maybe I didn't explain it enough. We actually don't use the labels, and we just look at the overlap of the objects to see in the three-dimensional space to see if they're interacting or not. So in fact, we are kind of doing this weekly supervised method, but I think it's just either or. I mean, okay, not either or, like it's not nice to rely on those labels. This is why we didn't really do it. And also, I think the problem is that these supervised models have issues in working outside the data set that it was trained on. And this is yet another reason why we just kind of went geometric and kind of build on this common sense kind of priors.
Okay.
So can I ask one more, or are we out of time?
Yeah, please go ahead, man.
So I'm not an expert on this RL stuff, but I find the results really appealing. This loss function where you're really trying to match the captured motion, that feels like it pulls you away from a generic solution. And so there must be some trade-off between a generic physics solution and matching this motion. How do you decide how to balance that? Well, because if you match this perfectly, then you're only going to get this one motion, and I think, and it's not going to be stable to perturbations or something like that. Is that right?
Yeah, so then I think it becomes like, this is where the reward, I'm not an expert in the reward RL, but this is where like the issues of the reward, what's the word? The reward balancing kind of comes in, right? It's just a matter of how much weight do you put on top of this reward as opposed to everything else. So this is why this motion tracking objective is not really good. And another reason it's not good is you have to actually know the phase, like you have to align it by the time, and so it's like a physical phase thing. And at every single phase, you have to do this particular pose, which is a measurement. And so while Deep Mimic is really cool, it's kind of like RL-based motion trajectory optimization is how I basically see it.
Right.
This is why the newer work is kind of more exciting because it frees you from this like phase synchronization, but doesn't give you like crazy motion through this kind of learned reward on the style, basically.
Okay, that sounds pretty important because also Sebastian Starke's work required all of this phase segmentation and stuff, and that was a terrible, long, slow process. So this would be cool. I'll check out AMP then. It's great.
Thank you.
Thanks, Angjoo. Super talk.
Thanks, Angjoo.
Writing down AMP.